Diffraction and interference of light. When waves meet an obstacle, they bend around it. This phenomenon is called diffraction and explains why you can hear a person around a corner even though you can't see them. When waves meet a small opening, the opening generates a new wave on the other side. The picture shows a wave moving from right to left. When waves meet an obstacle, they bend around it. When waves meet a small opening, the opening generates a new wave on the other side. So here we can imagine this being water waves, and we have a wall that extends out into the water, and the waves will just bend around the edge like that. And here, if you have a really small opening, you end up getting rounded waves. Even if they come in as plane waves this way, they'll end up being rounded on the other side of the opening. It was observed that light bends around objects. Light that is shown on a coin creates a shadow behind the coin, but in certain cases, depending on the light's wavelength and the coin's size, a bright spot would show in the middle of the shadow. This is not to scale at all, but it's just to show that with certain distances from the light source to the coin to the wall here, you might get a bright spot in the middle of that shadow. This phenomena is based on Huygens' principle, which states that every wavefront, shown here on the right, is actually an infinite line of point sources. As shown below, a line of infinite point sources will end up simplifying to a plane wave. A plane wave is just a straight line representing a wavefront. So here we start with 3 point sources. They'll look like this, rounded waves. Here you get 5 point sources. The more point sources you have, the straighter this line gets. When a plane wave hits a wall with a small opening, you can imagine that just one of those point sources, remember there's like an infinite number of point sources, just one of those is going to get through it. Once it's through the slit, there are no more point sources on the left and right sides to interfere with, which is why the wave is going to propagate outwards as though there are no other point sources interfering. A wider slit will let a few of the point sources through. This will cause a flat plane wave in the middle, shown here, but then radial spreading at the edges, shown here. Since there are multiple point sources, they will interfere with each other. We will look at single slit interference a bit later. For now, let's examine how waves interfere with each other on the next slide. The superposition principle says that when two waves pass through the same point, the displacement is the arithmetic sum of the individual displacements. If two waves are in phase, they add together. As shown to the left, waves are in phase when the crests of one wave line up with the crests of the other wave. The troughs also line up. This is an example of constructive interference. So the resultant wave will have the amplitude here plus the amplitude here, giving us a very large amplitude. And the troughs also add up to a very large trough. If two waves are out of phase, they subtract from each other. This is an example of destructive interference. Shown to the right, the crests of one wave line up with the troughs of the other. So when you add this amplitude and then add this negative amplitude, they cancel out to 0. If two waves are partially out of phase, they subtract from each other, but not fully. This is an example of partially destructive interference. Shown to the right, the crests of one wave don't exactly line up with the troughs of the other. These waves partially cancel out. Below is a screenshot of 2 point sources, which are speakers creating sound waves. These waves are interfering with each other. Depending on the location, the sound you hear might be very loud or very quiet. This is a little tricky to read, but the destructive interference is shown in the gray areas, here and here in red. The constructive interference is shown in the black and white areas, like here, here, and here.